2.5 is significantly more simple compared to 2.4 because there's not this super long sort of meandering talking about like normalization, preservation, and all that stuff. This is actually just a very straightforward problem, so I'm not going to spend too much time on it. We're asked to find the expectation value of the potential energy for the nth stationary state of the harmonic oscillator. So we know that for any wave function, the expectation value of any physical value q is equal to the integral from negative infinity to positive infinity of psi star times the operator of q in terms of x and p operators acting on psi. So for a harmonic oscillator, we have that the potential is going to be equal to 1/2 kx squared, but since we sort of made the statement earlier that it's more convenient in quantum to work with omega instead of k, we're going to put this in omega, so this is actually equal to 1/2 m omega squared x squared. So the only term here that actually is an operator is x, and the x operator equals just x itself, so the expectation value of v for a harmonic oscillator is going to be equal to negative infinity to positive infinity, and they're specifically asking for the nth stationary state, so we're going to put psi n star times, and actually, you know what, we're going to move the 1/2 m omega squared outside of our integral because those are just constants, so 1/2 m omega squared, and then we have x squared times psi n dx. And the problem here is that we don't necessarily know the general form for the nth stationary state of our harmonic oscillator. The way we've been constructing it so far is that we have the ground state, psi naught, and we get higher states by applying the a hat plus operator. So in order to sort of rectify this, the proposed solution that Griffiths gives is to actually define x and p hat in terms of the a hat plus and a hat minus operators. So we have a hat plus minus is equal to 1 over the square root of 2 h bar m omega times minus plus I hat p hat, or not I hat, but just I times p hat. And then added with m omega x. And Griffiths tells us that we can actually reverse the relation and define x and p in terms of a hats, and we'll get that x equals the square root of h bar over 2m omega times a hat plus a hat minus. And in the same vein, p hat is actually equal to I times the square root of h bar m omega over 2 multiplied by a hat plus minus a hat minus, and you can plug these two back in. So you can plug the a hat operators into x and into p to verify that this is in fact true. And if we sort of shove this in, then what we get is, well, we only have x, so v is going to be equal to, and we have the 1/2 m omega squared at the start, and then we have this sort of constant term at the front that gets squared, so times 1 over 2 h bar m omega, and then our integral from negative infinity to infinity. Whoops, I'm sorry, that wasn't right. This constant at the front is actually for x, so h bar over 2m omega. And then to positive infinity of psi n times, and let's see, so x is a hat plus a hat minus. Times, and let's not forget the complex conjugate, psi n times dx, and then we're squaring this because it's x squared. So from here, we can eliminate the m, the omega goes to first power, so this equals, let's see, h bar omega over 4 times the integral from negative infinity to positive infinity. And we have psi complex conjugate. And then if we expand this out fully, we get a hat plus, or a hat plus squared, plus a hat minus, plus a hat minus a hat plus a hat plus squared, or a hat minus squared, apologies. And the reason why we're writing it out, so first off, we did this by just using distributive property. A plus b squared is a squared plus 2ab plus b squared. The only difference here is that we're sort of differentiating between a times b and b times a, because remember, operators don't necessarily commute, and we've already seen that in the case of the a hat operators, they do not in fact commute. So these two are different. And then we multiply by psi and close off the integral with the dx. So this is actually 4 integrals. We can write out 4 separate integrals. The first one would be psi star times a hat plus squared times psi. The second one is psi star a hat plus a hat minus times psi, etc., etc. Right away, in 2.4, we sort of showed that orthonormality still applies to the harmonic oscillator. So instantly, the a hat plus squared and a hat minus squared terms go to 0, because those acting on psi will give us, like, this will be psi n. If these are both psi n, then we'll have the a hat plus squared will give us, something multiplied by psi n star times psi n plus 2, and since they're not the same energy level, they're orthogonal, and their integral goes to 0. Same thing for the minus, but it'll be n minus 2 instead of n plus 2. So we're just left with the a hat plus, a hat minus, and a hat minus, a hat plus terms. And we already know how these act on psi, because we proved in 2.4 that a hat plus times a hat minus acting on psi n is going to give us n times psi n. And we also know that a hat minus a hat plus times psi n is going to give us n plus 1 psi n. If you don't remember these relations, they are from example 2.4, so please look at that. So if we plug these in, then our integral becomes h bar omega over 4 times the integral from negative infinity to infinity of psi n star, and a hat plus a hat minus acts on psi n to the right. So we have, let's see, n for the a hat plus a hat minus, and then we have a hat minus a hat plus contributing an extra n plus 1, and this on to psi n dx. This is a constant, so we can just move it outside of our integral. So we're left with psi n star times psi n. And since psi n is by definition normalized, this integral just goes to 1. So we're left with h bar omega over 4 times 2n plus 1. And we can make this a little bit neater by distributing out the 2. So then this becomes h bar omega, and the 2 cancels out with the 4 at the bottom, becomes over 2 times n plus 1/2. And in comparison, as a point of interest, we note that the sort of energy values, aka the total energy values for the nth excited state, is actually h bar omega times n plus 1/2. So what this tells us is that the expectation value of the energy is actually half of the actual energy for any given sort of energy state of the harmonic oscillator. And this is something that is unique to harmonic oscillators. It doesn't have that much significance now, but it does play a role later on in chapter 3 when we sort of start introducing linear algebra. So for now, we can just keep this in mind.